Morning, everyone. So yesterday we introduced our main electrochemistry table. Basically, all the reactions are written as half reactions. They're written as reductions. We'll see a little bit more in terms of the voltage that we saw on the right-hand side there. But pretty much, different chemicals have different abilities to gain electrons. We're going to start from the bottom left of the table. Those are the best guys that reduce. You're going to find your first match on that side. We're going to start from the top right and start working downwards. First match there will be the one that gets oxidized. Everyone else will therefore be spectators. So just for a quick practice, just in reading the table. So warm up. I want you to just state balanced equations for the spontaneous reactions. Okay. And I'm going to work through this with you here. When you look on your table here, we basically want to make sure that the reduction, half reaction, reduction occurs lower than the oxidation. Okay, so as we step through some questions, we'll see what we mean. So first step, I'm going to give you a mix between aluminum metal is placed in a 1 molar solution of FeI3. 2, let's do a reaction where I bubble in chloride gas, bubbled into 1 molar NaBr. And let's do one more, 3. I'm going to bubble in hydrogen gas, bubbled into 1 molar. I'm going to use terminology here, acidified. It just guarantees, yeah, we have H plus present. Acidified Li2SO4. Okay, so I encourage you just to pause the video. You can try it out for yourself. Okay, I'll give you a hint. First thing that you do for the rest of this chapter is I want you to make a list of exactly what you have. Okay, so in this case here, let's do it for these first 3. First one, I have aluminum metal. That means I have aluminum solid. I do not have Al plus 3 ion, right? I have 1 molar. That molar is sneaky. That molar means it's a solution. That means we also have water. Now, for the most part here, we're going to find other things they've reduced or oxidized before water. We're going to come to a type of cell later on that water interferes like crazy. So be really careful. Yeah, whenever you have 1 molar, it's definitely going to be water present. This FeI3 is a salt. This one here will be broken up in solution. We have Fe plus 3 ions, and we have iodide ions. What I do not have is I don't have Fe plus 2. I don't have Fe solid. So if I see those on the table, I need to skip over it. I don't have an I2 as well. Similarly, for the other 2 here, I have chlorine gas, so I have Cl2. This is bubbled into 1 molar. Again, we have water. We have NaBr, so Na plus and Br minus. All you're going to do is you're just going to make a list of exactly what you have. Hydrogen, we have we have water, and then the acidified tells you we have H plus. Lithium sulfate, so I have Li ions and I have SO4 minus 2 ions. Okay, that's always your first step, because when you actually look on the table, I want to know what I'm going to stop at. Again, on your table, the strongest guy that's going to reduce is the one that's lower left. So I want you to start on the lower left and go upwards. Let's do this first one. We're looking for any of these 4, aluminum, water, iron plus 3, or iodide. Okay, so let's just go up here. Right, I run into aluminum plus 3. Well, I don't have aluminum plus 3, so that's not going to react. I ran into water. Okay, I ran into iron plus 3. Let me just put a box around them when I find them. So Fe plus 3 and iodide. Nope, I don't see it on the side here. Okay, so as I started out from the bottom left and going upwards, so I don't have F2, I don't have these ones here, don't have the dichromate, oxygen, or anything. Oh, I have iron. Once you find your first match, that's going to be the reduction. So I can write that right away for part A. The reduction is going to be Fe plus 3, and an electron is going to one-way arrow become Fe plus 2. We're going to deal with the charges, the voltages a little bit more in today's lesson. That voltage is 0.77. On the table, it's reversible, but once you know this is the guy that gets reduced, it's a one-way arrow. Okay. Once you find out the guy that gets reduced, even the water there is just going to be a spectator. It can't do anything. Okay. Then you start from the top right. These are the best guys at coming backwards, at getting oxidized. Again, they try to confuse you. They call this the reduced species. Currently, it's reduced, but reading right to left, it's becoming oxidized. So oxidation is going to the left. As you go downwards here, again, you're looking for your matches here. Oh, I do run into aluminum. I run into iodide down here. I run into water. You'll notice water shows up a few places. Water has been used for balancing, but because we need all the chemicals here, if I don't have this H2SO3, I can't run the reaction. I wouldn't stop there. Later on, when I'm dealing with the water reaction, I'm just going to deal with reactions that only have water inside it. So we have those ones there. Do you see any other matches? I had an Fe solid, but I don't have Fe solid, so I had to skip over it. Again, it's the first match that you find. Oh, I found aluminum first. Let's go to the left side. I'm just going to rewrite it. Aluminum is going to become Al plus 3 and 3 electrons. And the voltage going left to right, it was negative 1.66. Going right to left, it's going to be positive 1.66. Remember, the half equations on the table are already balanced for you. So we just need to do a lowest common multiple step here. I need to triple this first reaction. Long story short, the voltage does not get tripled. So we're going to just, for the first reaction, 3Fe plus 3. And an aluminum is going to become 3Fe plus 2. And we have aluminum ions. What's the voltage going to be in total? The first one gain 0.77. The other one gain 1.66. I'm just going to add these two here. 1.66 plus 0.77 gives me here 2.43 volts. And what we're going to find is if this overall, this is called the voltage, the E cell. If this voltage is positive, it implies that this one here is spontaneous. Okay, so let's try the second one here. Again, I made a list of all the chemicals that I have. We're looking for exact matches. So I have Cl2, I don't have Cl minus, okay? So I'm going to start from the bottom left and start going upwards. As you go upwards, oh, I don't need to go too far. I already found chlorine, perfect. I don't care if I have water in solution because this one here is so much farther up the table. This is so much worse at reducing than the chlorine. So the chlorine is going to do the reducing. I'm going to write out that reaction. They have a pesky little half there, so I'm just going to copy it out. Half of chlorine as a gas and electron. One-way arrow becomes Cl minus. This happens at a positive voltage 1.36. That's going to be called the standard potential today. Then we look on the other side here on the right side. Start from the top right and go downwards. Do I stop at sodium? Well, I have Na plus ions. I do not have sodium metal. Nope. It's as if I don't have that. Let's just keep going downwards, right? Sodium plus would actually try to reduce, but that's actually even worse than water. So you keep going downwards here. Let's see when we find our first match here. We need to go all the way down the table. In fact, we're going to get pretty close to water, but we actually have bromide actually oxidizing first, okay? So once you find your match here, anyone else is a spectator. So therefore, the reaction is just going to be the bromide from this solution. The Br minus is going to become half our Br2 liquid and an electron. The voltage positive 1.09 was quoted for left to right. As I flip it around, I need to now go negative 1.09. Again, we have a spontaneous case. My reduction reaction, this half equation is occurring lower than my oxidation reaction. Because they have not crossed each other, we're going to still have a positive voltage, albeit it's not that big. So I'm just going to write this reaction here. You're going to bubble in chlorine gas here into a bromide solution. This becomes chloride ions, and then we're going to just bubble off bromine. We can even do the voltage for this here. What is 1.36 minus off a 1.09 gives me here an overall voltage of 0.27. Okay. Well, what about the sodium? Where did it go? Normally, this single replacement reaction would have looked like we had Cl2 bubbled into NaBr. You would have checked the activity series. Well, chlorine here is smaller than the bromine. Chlorine is a more active one, can kick off bromine no problem. We're going to end up having Na and Cl, and Br2 ends up getting kicked off. So we can predict it just based on the periodicity stuff we learned last year. There's also a color change here. Chlorine here is typically like a yellow-green sort of gas. Bromine here is more like a red-brown kind of liquid. So it would definitely come with a corresponding color change. So what about the sodium? Sodium had already lost its electron to bromide. This was Br. Sometimes they even show the table here. Br actually has a negative charge like that. Sodium has still lost a charge to the chloride. Okay, so sodium is just a spectator. It would have been canceled out overall. Let's do this third one as well, just for completeness sake here. Again, a starting step is always good. Just make a list of exactly what you have. I have H2, water, H+, lithium ions, sulfate ions, and it's just a matter of trying to find some of these on the table. Okay? The more practice you get, the more comfortable you'll be. So as you go up here, we're going to talk a lot about this H+ reaction in today's lesson. We had the water from before. Li+ is not really good at reducing. We have sulfate. Now notice that this sulfate reaction, yes, I need the sulfate to react, but I also need it in acidic solution. if they did not specify this acidic, and if I did not make mention that I have H+, just because I have sulfate, if I don't have H+, I wouldn't be able to run this reaction. This time, fortunately for us, we do have sulfate and we do have the H+, so yep, that's a go. I think that's all on the left-hand side here. On the right-hand side, I believe we only run into H2, okay, and water a little bit lower, okay. So you always start from the bottom left because these are the best guys that reduce. So you go uppers, you want to find your first match here. Just want to double check I didn't miss anything here. Yep, it looks like it's this sulfate reaction. We're going to go sulfate, SO4 minus 2. It has to be acidified or acidic conditions. Again, on the table, it's written left to right because depending on your exact combination, maybe it's reduction or oxidation. But once you tell me, nope, this is reduction, do a one-way arrow. This becomes H2SO3, and then it gives off water as well. The voltage corresponding is 0.17. That's the reduction reaction. All these other guys that potentially could have also reduced, they don't get to reduce, they're spectators. Let's start from the top right and go downwards, find your first match here. So as you go downwards, I have lithium ion, I don't have lithium solid, so skip it. So keep going downwards here until you find your first match. Just let me do a double check here. I have H+, I don't have H2. Okay. I have H2 here, but this H2 here also needs hydroxide. I'm definitely in acidic conditions, so this reaction is out of luck. So we have to just do the hydrogen reaction. It's written right to left, so I'm just going to rearrange it here. So I have half an H2. I'm going to do a one-way arrow, so right to left. This becomes an H+ and an electron. The voltage going left to right was 0 volts, so going the other way here, -0 is just going to be 0, just 0 as well, okay? We're going to need to do a lowest common multiple. So the half equations are balanced. We just need to do a lowest common multiple step. So times 4, and basically the electrons, times 2. Basically then the electrons end up canceling out. Okay. So the spontaneous reaction, again, has the reduction reaction occurring before the oxidation reaction is lower than. This is going to be spontaneous. These are going to be the first types of reactions that we're going to see. So as I just want to completeness sake here, just write that all out. So we have sulfate. We had the 4H+ from earlier. The 2 times half ends up giving you just H2. This becomes H2SO3 and water, and then we're going to have 2H+. Because these half equations were already balanced to begin with, I would expect that this is already balanced, with the exception sometimes the H+s. So I have 2 there, I have 4 there. Let's just get rid of 2. I can ask you for what do you see happen around the electrodes. Because the reaction is actually losing H+, we're actually becoming less acidic. For the other chemicals here, the H2SO3 is aqueous, so that's not going to show anything. I had to bubble in gas, so it's going to be bubbled into solution, but then it becomes aqueous, and again, I also don't see anything. So more on those physical observations in today's lesson. Okay. So we're just going to get a lot more practice using this table here, making a list of the chemicals that you have, and then finding your matches. Okay, so let's get into a little bit of new stuff for today here. In the past, they used to call electrochemical cells just the umbrella term. So the sort of new way they're highlighting it here, we have an electrochemical cell. An electrochemical cell is actually 2 different types of cell. The first type of cell we're going to refer to is called a Voltaic cell or a Daniell cell. And this one here is basically how a battery works. For a Voltaic cell, what we're going to do is we're going to run a spontaneous, right, that's what we just practiced, a spontaneous chemical reaction to produce electrical energy. Right, that's what batteries, that's how they function, okay? After we did all the details of Voltaic cells over the next class or so, we're going to then switch over to something called the electrolytic cell. They used to call electrochemical is the Voltaic cell. Now electrochemical is the umbrella term. It actually captures both of these. And electrolytic cell is actually a non-spontaneous reaction. This is sort of like, oh, I have a dead battery, and now when I plug it into the wall socket, I want to recharge this battery here, and I want to use electrical energy to run. Because the chemistry was non-spontaneous, the chemicals don't naturally want to go that way, we're going to use electrical energy to run our reaction. So it's sort of the other way. It is this interplay between chemical energy and electrical energy. First one was changing chemical energy into electrical. After we do that, we're going to do electrical energy, use that to actually do chemical energy or chemical reactions. Okay. So for the first little bit here, again, we just need to switch the name here. They used to just call it an electrochemical cell. We are actually just talking about a voltaic cell right now. Okay, that's the first type of cell. Okay, a voltaic cell can also be called a galvanic cell, also called a Daniell cell. Okay, basically it uses a spontaneous redox reaction. It uses chemical energy to actually convert it over into electrical energy. This is basically a battery, right? So we're going to see what are the sort of ins and outs in using the table here. We're going to look at this one in detail. Imagine that you have a copper rod and it's immersed in a copper sulfate solution. Right? So I have one beaker. Right. You have a table picture of it down below as well. But I have one beaker. It contains copper sulfate, and it has a copper rod. So copper would be solid. Again, I hinted at it yesterday. Usually, if you have an electrode made out of a certain metal, you usually surround it with ions of that metal as well. So I have a copper solution, and I have a zinc solution. So a zinc strip, so it's a zinc solid, it's in a zinc nitrate solution. Why nitrate? Well, we remember nitrates are very soluble, copper is also very soluble. So if I were making a state of sort of what chemicals that I have Zn plus 2, I have nitrate, I have Zn as well, so I have the metal plate. On the right hand side here, I have copper, I have copper ions, Cu plus 2, and I have sulfate ions, those are completely dissociated, and I also have water. They're not going to interfere too much with our first voltaic cell. So what are the respective half reactions? So what if we just did the same sort of practice, used our table, and tried to find out what our reactions are going to be? So again, what we're going to do, we're going to start from the bottom left, and we're going to go upwards. You're going to find your first match. You go upwards, I run into the copper reaction. I run into this copper reaction before the other copper reaction, so this is the reaction that goes. I don't run into zinc until later on. Zinc ions are spectators. As I start from the top right and go downwards, I do have zinc solid, so this is actually going to be the oxidation. I do run into copper solid later on, but copper solid is not as good at oxidizing. So what I'm going to do here is I'm just going to rewrite these reactions for you on the notes here. So the respective half equations, we actually have Zn plus 2 and 2 electrons. On the table, it was reversible, so I'm just going to show the reversible for now. This becomes zinc. The voltage is at negative 0.76 volts. We don't run into the first copper equation until a little bit later. This becomes Cu, and this is a positive 0.34 volts. Those are the respective half equations. Those are already balanced. Again, just like we practiced on the table, you start from the bottom left and go up. Oh, I find copper plus 2 before Zn plus 2, so therefore, this reaction is a forward reaction. This is the reduction reaction. As I start from the top right, try to find out who's oxidized, I run to zinc before I run to copper. So this is the one-way arrow. That's actually the direction that we're headed in. Okay, so let me just jot that out for you here. So the Cu plus 2 is actually going to gain 2 electrons, become Cu. That's a positive 0.34. When I flip this reaction around, I write zinc on the left-hand side. Zinc is going to ditch its electrons, become Zn plus 2 and 2 electrons. Fortunately, the half equations are balanced. Even lowest common multiple, they're already balanced off. These 2 electrons end up canceling those 2. So therefore, our balanced equation is copper ions and zinc are going to become zinc ions and copper. Again, we're going to come back to do voltage later on, but basically it's going to be an add of these 2. This was the reduction potential, it was negative. When I flipped it around, this one here is actually a positive 0.76 volts. So positive 0.76 plus positive 0.34. This one here ends up giving you 1.10 volts. So E naught is equal to 1.10. This is like a battery that generates 1.10 volts for me. Okay. So that's the spontaneous reaction that occurs. We've been able to calculate that, no problem. What I want to just sort of hint at, the way we set up yesterday was we had both rods sitting in the same solution. Okay, so we had the zinc and we had the copper, we had the zinc ions and we had the copper ions. Well, what actually reacts between copper ions and zinc ions? Copper reduces better. Copper is going to gain the electrons. Who's ditching the electrons? Zinc oxides before copper does. So zinc jumps into solution, becomes Zn ions. Those ions have nothing to do with these Zn ions here. They ditch the electrons here, and then the spontaneous reaction has copper swim up close to this metal plate and then solidify as copper chunks. Right? It's going to be copper-plated zinc later on. That is definitely a spontaneous reaction. Definitely the electron has transferred. The only problem is I have not been able to taper off the electrical energy. I know electrons have passed from the zinc to the copper ions, but I haven't managed to actually tap that electron flow. So what we're going to do here is kind of cleverly here, as I sort of alluded to on the right-hand side here, we're going to set this up in two separate containers. We're going to have half of the reaction occur on one side, the other half of the equation occur on the other side. It's the same spontaneous reaction. Identical, it's going to generate a positive 1.10 volts, but we're going to force the electrons to travel through a wire, and that's actually where we're going to be able to taper off the electrical energy. So hopefully on your notes page here, these beakers show up a little bit better, but same thing is going to happen. We have two separate beakers. We have our solutions containing exactly the same mixtures as before. We looked on the table, we knew the reactions. The zinc is willing to jump off into solution, drop its electrons off. So zinc solid is going to jump off. It's going to drop off its electrons here just like it did before. But because copper is not in exactly the same vessel, the copper is over here. Copper can't actually swim over here and actually pick up the electrons. What we're going to do is we're going to actually connect them with an external wire. Because these are electrode plates, these ones here are going to allow for electrons to flow. The electrons that are dropped off by the zinc, as zinc jumps into solution becoming new zinc ions, the electrons build up on this plate, and they're actually going to travel down the wire. They're going to arrive at the other half cell, and copper can then swim up close to the electron plate and basically solidify on top of its surface. So what I want to show you here is it's exactly the same reaction, but we're forcing the electrons to go through a wire. We actually have electrons flowing in one direction. As long as we have a current flowing, this is where we can run our light bulbs, our devices. I can actually taper off the electrical energy. We're going to say in general, okay, so electrodes. Electrodes are essentially our conducting metal plates. There's two different types of electrodes. The one that does oxidation, we typically refer to it as an anode. Although be really careful with this definition, the anode is the location, it's the site of oxidation. It's where the oxidation occurs. So in this case here, the zinc itself is the anode. The zinc itself is actually doing the oxidation. We can have other reactions later on. Maybe the zinc plate actually doesn't do anything. Maybe another chemical swims to the surface and drops off its electrons. As long as it's the whereabouts of where things lose electrons, it's still called the anode. This is where there's a loss of electrons. The electrons flow through the wire. They always flow anode to cathode. That's the name for the other one here. Cathode, that's actually where we get our words anion and cation from. Cathode, similarly, is the site of reduction. Again, some more corny acronyms for you here. You can say an ox cared, right? And therefore, an anode is oxidation. The cathode is the site of reduction. Okay, so somehow memorize these things for yourself. We see here which directions the electrons flow. Electrons flow in the wire. Okay, they always like testing this here. Do electrons actually jump off into the beakers? Nope. Electrons will only flow from being dropped off at the anode. They're going to flow through the conducting wire to the cathode. They already get picked up by the copper ions. They solidify out, and therefore there's no free electrons in nature. Electrons flow in wire from anode to cathode. And even as we get to more complex situations over the next couple of days or so, that will always be true. Electrons flow in one direction. We've created a direct current circuit, a DC circuit. Okay? So actually, they flesh this out a little bit here. The conductors, metal rods at which the half reactions occur. Half occurs on the left side, half occurs on the right side. The oxidation half is the anode side. And then the reduction half, and ox cared, so this is the cathode side. The metal rods themselves are generally just called electrodes. They're just a temporary conducting surface that actually allows electrons to be deposited there shortly. We said here, this is a really important conclusion, anodes flow from anode to cathode. And again, I'm going to add here through wire. Okay, sometimes they even call it an external wire. Okay, they do not go into solution. So not in solution. Okay, it's the ions themselves that we're going to see shortly that complete the circuit for us. But we've set it up in such a way we're running exactly the same reaction as we had pitched earlier. Earlier, the electrons transferred way too quickly, and we couldn't actually taper off the electric energy. Now that I actually separate into two containers, I force the electrons to flow from one side to the other side. It's this current that it's actually going to give me my electrical power. So at the very least, for a voltaic cell, a Daniell cell, a battery cell here, you're typically going to see two beakers. If anything, maybe one beaker, they can have a membrane in between, but there should be two distinct sides on it. Okay. Let's imagine we went into the lab and we did exactly this. I set up the zinc solution, I set up the copper solution here. I'm fully expecting, the electrons flow through this wire here. We put it, huzzah, nothing's going to happen. This is not going to be a battery. The one major problem with the electrochemical cell, you don't need to memorize this, you can actually see it from the reactions. Well, on the left side, we have our zinc. It's supposed to be ditching the electrons, dropping off electrons. It's suddenly jumping off solutions. We're going to have a lot of zinc ions extra in this beaker here. This left-hand side beaker is at risk of becoming overly positive. So the one major problem here is we're going to have positive charges accumulating at the anode side because we're actually creating way more Zn plus 2. And similarly on the other side, it's not obvious, but our reaction involves taking copper ions. Copper ions are going to grab the electrons that arrive there, and they're going to reduce to become copper solid. The mass is actually going to increase, by the way, because we're getting chunks and chunks of solid on the top there. We have a negative charge that's actually going to accumulate at the cathode side. Why negative is because I'm actually losing. So losing Cu plus 2, right? They're gaining electrons, they're neutralizing, and therefore the charge is actually coming downwards. So I want you to think back to equilibrium here. If there's an excess of Zn plus 2 around the electrode, then the tendency is actually going to drop. So the reaction that we're interested in looking at is the zinc is supposed to become Zn plus 2 and 2 electrons. That was the more favorable oxidation. And yet, if we're going to end up building up zinc, because all these reactions at the end of the day are in equilibrium, as this concentration goes upwards, it's actually Le Chatelier that's actually going to shift it left. It's going to actually prevent the zinc from actually oxidizing any further. So let's write that down in words here. The Zn plus 2 ions shift the equilibrium left, making the oxidation less favorable. So between the zinc and the copper, zinc was better at oxidizing, but even this half reaction is having trouble. Similar problem here on the copper side. We wanted the copper ions to pick up the electrons as they arrive through the wire. We want them to solidify as copper. As I gradually lose copper, the concentration of copper drops here. The Cu plus 2 ions decrease. They're going to shift the equilibrium also left based on the way I've written it, making the reduction also less favorable. Okay? So far as I pitched it here, the half reactions look good. We found the better reducer, the better oxidizer, but nothing's going to happen because both sides are at risk of accumulating charges. That's another way of seeing this part here. We cannot have free charges. We had said we had to balance out the electrons. They can't be free in nature here. Cannot have free charges accumulate in nature. Okay? Because charges are unstable. If one beaker became positive, the other beaker became negative, these beakers would attract one another. Eventually, it'd be large enough to overall stop the electron flow, so no battery would be working. How can we actually establish it? How can we actually solve this problem? How can we actually demonstrate a working battery? All that we actually have to do, we're going to still have the same beaker, so you can flip over the page. We still have the wire. We're proposing the zinc solid here is actually jumping off in solution. It's generating new zinc ions. How can I stop this side from becoming overly positive? Well, let's put in another solution that's negative to counterbalance that. So what we're going to do, we're going to add what's referred to as a salt bridge. It's a U-shaped container, and basically it contains an ionic compound that has charges to counterbalance your charge for you here. So we're going to add a salt bridge to maintain electrical neutrality. That's all that it wants to do. So it could be a U-shaped tube, the real U-tube. Okay. Usually we fill the solution here. 1 molar we're going to see a lot for our standard conditions later on, but usually we're going to use like KNO3. I just need some neutral salt. Okay, I definitely don't want to hydrolyze. You can check your acid-base chapter, they don't. And these ones here, if you actually check your electrochem table, these ones here pretty much are inert ions. They're not really good at reducing, they're not really good at oxidizing, so they probably won't interfere with the reaction that we actually want. All we need, however, is the KNO3. Great, it has K ions, it has nitrate ions. because this solution here is at risk of becoming overly positive, the nitrate ions in this U tube is actually going to jump down to that side. We're going to have a generalization here. We have the negative ions, or anions, actually move towards the anode. On the other side here, we have copper ions. As copper ions grab electrons that arrive here, they solidify on the surface, they start getting reduced. Our charge is steadily dropping here. It's actually the K plus in solution that's actually going to go downwards, and as K plus, it's not actually going to react, but it's just going to maintain some electrical neutrality for me. Cations generally move towards the cathode. And actually, depending on the size of the ions themselves, even these NO3 minus ions here, they're going to help, okay? But I need to have extra NO3 minus to counterbalance the extra Zn plus 2 that I have, okay? We have sulfate here. That's also an anion. The sulfate here would also try to swim through the salt bridge, but probably the sulfate is too large a molecule to actually get all the way through. It has trouble actually getting through the salt bridge. We're probably really just relying on the nitrates to actually get over, okay? We can make some physical observations at each of the electrodes as well. So far, we had said the reactions are zinc jumps into solution, becomes new Zn plus 2 that's being neutralized here in 2 electrons. So we're going to lose solid zinc. The mass of my anode increases. The mass, decreases, right? I'm losing solid particles and this jumping into solution. Whereas on the other side, the copper ions are actually solidifying out as new, fresh copper solid. And therefore, on the metal plate that already was copper is now being coated with another layer of copper. In this case, the mass actually increases. Again, that's not something you need to memorize. You can just see it directly from the equations themselves. Sometimes we actually have a gas that's forming, so you can say there's bubbles that are forming underwater. Sometimes we end up generating H+. We can say it's getting more acidic. We just wanted to see what reaction is going to be. Okay? So the net movement of the electrons, the negative charge from anode and cathode, is offset by the ions in the salt bridge. The ions effectively complete the circuit. Remember, electrons flow anode to cathode. It's the ions in solution that just counterbalance the charge. Okay? One more note here. So the anode, in terms of mass, we just said it decreases in mass. We're losing solid zinc, where the cathode actually increases in mass this time here because copper solid is actually plating out onto the electrode surface. Okay? Electrons are going to flow until the solution is completely depleted of ions, or until the electrode plate itself actually erodes. Tomorrow we'll flesh this out a little bit more here. We're going to take another look at that E cell, this E voltage, and then we're going to practice a few other sample problems. Let me know if you have any questions. Thanks, guys.